Hello everyone, and thank you for attending today's webinar, Achieving Autonomous Driving with Simulation and Testing, presented by Spirent Communications. My name is Romain Zimmerman. I'm a Business Development Manager for the Positioning, Navigation and Timing Division at Spirent, and I'll be moderating this webinar today. Our speakers are Dr. Raphael Grech. Raphael is Business Development Manager for Connected and Autonomous Vehicles, and AJ Muru. AJ is Product Manager, both at Spirent. So before we begin, just a few technical notes. So if you'd like to download the slide deck, please click the resources button at the bottom of your screen. There are also other links there that you may find useful, including case study and blogs. The webcast is being streamed through your computer, so there is no dial-in number. For the best audio quality, please make sure your volume is up. This webinar is being recorded and will be available on demand within 24 hours after the event. And time permitting, we will follow the presentations with a Q&A session. Please submit your questions using the questions and answers tab to the right side of your screen. Okay, now let's begin. Raphael, please go ahead.
Hello and welcome to our webinar. Today I'll focus mostly on position navigation and timing in a connected automated world. With more connected vehicles and autonomous vehicles coming into our environment, these systems tend to rely or will have to rely more on their position accuracy, especially when different entities are communicating and talking to each other and expect to work together. One typical example is ride-hailing applications where a user and a cab driver need to understand where each other is so that they can fulfill their service. When we have self-driving vehicles, it becomes of critical importance that the positioning is precise, and we would need to know exactly up to at least a meter accuracy where the other party is. When we have a more complex environment, then this meter accuracy becomes decimeter accuracy and even centimeter accuracy if the vehicle is fully autonomous and has to work in a complex environment. Also, what is very important with connected devices is the synchronization between the different entities working in the same environment. This is because whenever a position or a signal is sent from one vehicle, we need to make sure that the other vehicle has the same timestamp and they are related to a same common time. GNSS is the only absolute positioning system and is still considered the only formal positioning mechanism. And we can see this with the upcoming regulations with eCall and intelligent speed assistance. We also understand that GNSS cannot provide the whole positioning spectrum all by its own. So there are cameras, LiDAR, and radar techniques together with HD maps which would help the traditional GNSS and IMU for positioning. What is important to notice also that with these other sensors coming into play, the integrated systems need to be properly tested and validated together simultaneously to guarantee that there is a robust implementation. So why is there the need for GNSS? Traditionally, GNSS was used or is still used for positioning and localization, and we use it for navigation. But also, something which is taken for granted is the timing. Connected vehicles need to have a common time, and GNSS is the world timekeeper. When we refer to GNSS, the most common tends to be GPS. However, that's just one of the constellations. There are several other constellations, and they are all listed here. And the way that positioning is acquired is by something called trilateration, where we have 4 satellites, 4 equations for unknowns, 3 for the position and 1 for the time. And we get the position and the time from that. So how much do we use GNSS? How much should we trust GNSS? So Basically, everyone uses it, and it works. However, how much should we trust it? We see signs at times that GNSS shouldn't be trusted, our satnav shouldn't be trusted when we're driving around because things are not as they were indicated on the map. However, people still do some mistakes, or they follow the GNSS or satnav, blindly, and end up in awkward situations. So the question or the challenge that we try to resolve here is how can we make sure that connected and autonomous vehicles have a precise positioning and accurate timing and the environmental awareness. So with GNSS and the IMU setup, we can look at having precise positioning, and the other sensors like the LiDAR, the camera, can help us with the environmental awareness. If we focus on the precise positioning and timing, the main three factors are accuracy, integrity, and availability. By accuracy, we mean the nominal performance which defines the maximum allowable error for the operation. So how accurate the system is working. Integrity is the measure of the system limits and the probability of system failure. With availability is the measure of how often the system is operating within its boundaries and how much it is available. When working in autonomous mode, vehicles have to localize all the time, and therefore localization must always be available. So how important is positioning again for autonomous vehicles, and what should autonomous vehicles know about their position? So the three main questions would be: where is the vehicle, what's happening around the vehicle, and what does the vehicle need to do next? And what's important to remember is that an error of a few decimeters might position the vehicle on the wrong lane or on the wrong side, or potentially make the system put in a dangerous position that it might take a dangerous decision because of that. To make things a bit more complicated in a way, the environment that we would like autonomous vehicles to work in tends to be quite complex. And GNSS tends to struggle in certain areas, and therefore it needs to be tested and validated to make sure when the system is not going to operate in optimal performance. Some of the vulnerabilities of GNSS include spoofing, interference, GNSS segmentation errors, the atmosphere itself. Then we have cyber attacks and multipath. The most common that we see is multipath, especially in cities because of urban canyons. There's also interference, which is quite common, and to a certain extent, spoofing and cyber attacks tend to happen mostly on a malicious aspect when criminals would want to attack a vehicle or a system. One way of overcoming these limitations is, as I mentioned earlier, using additional sensors to increase the reliability and the redundancy of the system. Also, as I already mentioned, GNSS is still the only global positioning system that we have on this planet. All the other sensors are either local or relative. So it's nice and it's good to have all these sensors working together so that the GNSS would give the global position and it's reassured by the other sensors having the local and relative position. I want to mention some definitions now. So when I refer to positioning, it is the ability to measure where you are in space. With mapping is the ability to build a map. Localization is identifying where you are on the map. And finally, navigation is the ability to find a way going from point A to point B. So with global positioning, what we get is a number which gives you the latitude and the longitude. And since it's a global position, this point is related to a point on the world, and everyone on this world can relate to it. When we look at mapping, there are two main ways of having maps. One is a planar map, which is the one which we are more accustomed to, where you have a 2D map and you have potentially other layers on top of it indicating the road signs, the traffic, speed limits potentially, and we are also seeing that we might be able to see other agents on the map as well. With point cloud, what we get is a 3D representation made of millions of dots, where the localization would happen by having, say, a LiDAR, which is pulling in data from the world, and then it is correlated with this map. And finally, localization. So we know where we are on the map, we're given a position, and we can know where this position is on the map, and we can relate to it in the real world. So we know exactly where we are on the map and in the real world. If we have additional sensors like cameras, they would give us the environmental awareness, so we know what is within the environment that we see. And navigation, we would have two global positions, and we would need to find a way to get from point A to point B. Excuse me. And this is where the control algorithm 10 takes over by using the precise positioning to make sure that it can navigate from point A to point B. So in short, if we have local positioning and global positioning, local positioning tends to be used more for the reactive requirements of the system, say like defensive driving or collision avoidance, whereas the global positioning is used so that we can plan the whole journey. When we have GNSS, just GNSS, the maps are needed. If we have high definition maps like the ones with the point cloud, GNSS might not be required, but that's assuming that the maps have been built to enough high fidelity and they are related to some well-known location within the world. If we have imaging sensors and no LiDAR, for example, and no need for high definition and no high definition maps, then we would still need to find a positioning mechanism, and GNSS tends to be one of the ways which is provided. Also, there's a cost implications. So LiDAR at the moment and the maps related to LiDAR are still relatively more expensive to manufacture, to build, and to have the sensors on the vehicle. So we are seeing two trains of thought at the moment. One is having the more traditional, already available GNSS and imaging sensing, and the other one is having the point cloud and LiDARs. So yeah, we have to watch this space. And finally, we focus on the localization, but as I mentioned, we have the perception from the other sensors, which would give us the environmental awareness. We know where we are. We can plan how to get from where we are to where we want to be. And finally, there's the control mechanism, which makes us follow the trajectory which was planned. So as already mentioned, GNSS is required partly because of regulations. So there's the eCall, which is a requirement that when a vehicle is involved in an accident, it will have to use its position or send its position through a cellular network, and the emergency service will respond. And also intelligent speed assistance. This basically helps the driver to follow the speed regulations, and the vehicle would get, by using its position, the map, and by using cameras potentially to read the road signs, it would adjust the speed accordingly depending on the speed limit of the region. Again, this requires precise positioning, because if the localization is not accurate, the vehicle might think that it's on another stretch of road, and it might act differently than what's intended. Also, as already mentioned, that GNSS is not good enough for autonomous vehicles on its own. The thing to remember is that at present there is no one localization technology that can meet all the requirements for safe operation in all weather, road, and traffic scenarios. Also, the GNSS system is just one system or one subsystem of the complex system. The system is much more complex, with sensors, actuators, software applications, and algorithms. However, we have to point out that GNSS is still the only global positioning system, so we cannot fully make do without it. So GNSS tends to be traditionally integrated with an inertial measurement unit, so that when the GNSS position is either compromised or it's not accurate, it is backed up with the inertial measurement unit, which tends to be more stable. The only downside of IMUs is that it can drift because it's an incremental sensor. So other sensors might be required as well. Now, this graph is quite interesting because it shows that, as already mentioned earlier, no one sensor has the capability to provide accurate positioning in all conditions. And also, humans themselves, we have our own limitations. So if we have a complete system with several sensors, we have enough redundancy to make sure that the system would work in all conditions. One of these sensors, potentially one of the cheaper sensors, is cameras. These systems are very good at providing lane keeping and also object detection, assuming that you have the right algorithms in place. Then we have radar systems, which are very useful to provide the distance measurement between vehicles. And then there's LiDAR, which is a more expensive option. However, it gives a high fidelity data, which again, if properly worked on, it can give us some accurate results. And finally, with vehicle-to-vehicle communication, with all these sensors that we mentioned, there are still situations where the vehicle sensing capability is occluded or compromised, and GNSS and vehicle-to-vehicle communication, be it either through Wi-Fi or cellular V2X, would overcome this problem. What's important to mention is that with vehicle-to-vehicle communication, GNSS would still provide the position. It is still providing the position. And what's important to mention is that as the other sensors are tested quite rigorously, GNSS is no least, and it has to be tested and validated with the same rigor within the automated system. Now I'll pass the rest of the talk to AJ to carry on with showing you some of our solutions.
All right, thank you, Rafael. So now that Rafael has talked you through the high-level overview of CAV, Connected Autonomous Vehicles, over the next few minutes, I'll take you through our Spirent story, and I'll introduce you to some of the solutions that could prove very helpful in your development of connectivity and autonomy. Spirent is a truly global company with over 1,400 employees, serving a global customer base. Our market cap is close to $1 billion US, with over 100 issued patents. We've got more patents pending. The most important thing for us engineers is not the size of the company, but what's the value that we offer. So in that view, we consider delivering the testing capabilities that help customers manage complexity and overcome the challenges. Consider Spirent to be a singularly capable strategic partner for your never-ending journey. We marshal all our resources as a unified organization to provide integrated solutions tailored for our customers' needs. We try to adapt to our customers. We are not just dedicated to their quality, we are passionate about our customers' success. To be kept simple, we help assure our customers' promise to their customers. We at Spirent have multiple offerings addressing the needs of the automotive industry, starting from the connectivity to help you integrate the right connectivity modules. We offer various solutions like in-vehicle network test, setups for V2X, cellular emulation, and security auditing. We have everything that needs to get your connectivity modules prepared for deployment. On the topic of autonomy, we provide guidance on navigation, sensor fusion, and PNT assurance. In the next few slides, we'll focus on platforms we offer for your navigation test needs, as well as for sensor fusion. The positioning unit at Spirent is committed to provide you with the tools to solve your latest technology innovations. To make this happen, we have to innovate as fast as you, if not faster, starting from the design cycle through to the factory or production test needs. We have tailored our solutions to meet your needs. Our latest generation simulators have been designed with 30 years of experience, understanding and solving our customers' problems. Our record and playback system, that is the smallest in its class with a high depth recording capability, captures signals with very high dynamic range with respect to GNSS. Can't forget our services team that includes tailored and professional services, which complement our products portfolio. The purpose of our services team is to address your needs that cannot be served through just our products. As I mentioned earlier, our 30 years of experience and expertise has enabled us to design the best N-class GNSS simulators. These simulators create an RF that is just as real life as the real GPS signal outside. In the first few years, our GPS or GNSS simulator development, we got requests from our military users to develop inertial sensors as well that are coherent with GPS. This led to our inertial sensor model simulation. Today we can simulate GNSS and inertial sensors coherently based off a single clocking source. Further along the way, as we were supporting our high-end customers, we were asked to develop an RTK system. Now, as you know, RTK is the assistance-based server, so our customers really wanted to test both the station, the base station, and the rover. I can't even remember when we came up with RTK, but I can guarantee that this was way before our commercial users identified it as a technology that could get them to centimeter-level positioning for autonomy. In summary, we've had GNSS, inertial sensors, and RTK solution for a while now that has been tested for years by our high-precision GNSS users. Now, over the last few years, we've been hearing a lot of talk regarding the GNSS vulnerabilities, such as interference or jamming. There's spoofing, there's multipath, and so on. We knew there is no one better than us to help solve these issues for our customers. So we came up with software modules to address each of these vulnerabilities separately. So we have an add-on software for spoofing. We do have scenarios for GNSS. We do have scenarios for atmosphere. And then we do have another setup for interference and jamming. So over the next few years, we've had we had given very detailed thoughts on how to really address our customer needs for multipath. So we also came up with record and playback, because for multipath, there's nothing better than record and playback, because it records the RF environment as is, including interference and other fading, and then it can play back. There is no tool today actually that can provide better multipath than an RPS solution. RPS is nothing but a record and playback system. But you know, we've been around for quite some time, and it is usual to see interesting requests come by from our customers. And one of those interesting requests was about having a multipath simulation capability that can be controlled. No one had ever had a simulated multipath, truly realistic environment. So we thought about it, and then we started analyzing the different approaches, and then we started working with one of our current partners, Octal SE, who are experts at ray tracing. We worked them very closely. We provided the satellite and location and the user location information, and they provided the fading logic using ray tracing. We thought this is a great product in terms of multipath, because not only does it provide a multipath in a controlled environment that is better than the statistical models, but it also gives our users a visualization tool. So the users can really visualize what multipath is impacting the position and how, in which direction. So you can individually click, enable, disable the satellites, and then see how is the multipath impacting. And in addition, for autonomous activities, you can use that same tool for mission planning. So you can use our Sim3D, which is the tool that uses ray tracing along with GNSS. You can use that tool to understand how an area can be used for mission planning purposes. So the tool generates heat maps where over a certain period of time, and you can identify the good and the bad regions for GNSS coverage. Now, recently working with the automotive industry, we picked up on another such request, where the model of the car, very particularly the dynamics, was key for their analysis. Naturally, we are not motion experts, and we have no intentions of reinventing the wheel. So we started again looking for partners who have expertise in this field, and found players such as IPG, Octal, DSpace, and so on, and started working with them in a way so we can accept their motion models, and we can take that as a trajectory input, as a motion input, and create GNSS, inertials, and RTK simulation. Now don't forget, we can also do wheel ticks, and we can package all of the inertial or the wheel tick data over Ethernet, over CAN, over I2C, or SPI. It really is up to the customer to decide what format the data has to be transferred. For GNSS, we offer it over RF, whereas for IMU, we do have the flexibility to offer it over Ethernet, CAN, or I2C. We can even package it in the format of your interest. So now that we've looked at this overall block diagram, let's actually see in real life how do we apply and how does the actual setup look like. So in this slide, you can see DSpaces. This is an example with DSpace, but very similarly, you can use other signals or other third-party tools as well. All right, so you can see DSpace's motion desk on the very center with the car picture. Sim3D on your left with the 3D models of the buildings. SimGen, our software that controls the hardware boxes, and uBlocks receiver on the very right. The user can actually exercise real-time motion changes, and overall the system can quickly adapt to it. So you make a left turn on the screen using the steering, the car is going to experience a left turn. All the multipath is going to be impacted after taking the left turn into account. the entire orientation is going to change. So the multipath, the ray tracing, all of that has to be recalculated pretty much for every instance. All of that happens on a GPU. SimGen takes all of that fading information, it creates an RF and the other appropriate sensors, and then the RF part of the GNSS goes into U-blocks, and U-blocks is calculating the exact trajectory with limited multipath. This is what we call adding realism to simulations. Autonomous vehicle testing requires this realism to develop the right algorithms and deploy them. Okay, so this picture here shows our attention to detail. We've taken extreme care to use as many parameters as possible from the motion model inputs to generate the right RF signal and to generate the right sensor signal. The main objective through this integration exercise is not to lose on latency. We have by far the best latency that is offered by any GNSS simulator. And we're not just stopping here. This is what we can do today. GNSS, multipath simulation, spoofing, jamming or interference, automation. We can simulate IMU, we can simulate wheel ticks over CAN. We can record and playback RF signals in the 100 to 6 gigahertz frequency range, 100 megahertz to 6 gigahertz frequency range, including any GNSS signal. This frequency range can also record 2.4 gigahertz Wi-Fi or 5 gigahertz Wi-Fi and cellular frequencies. We work with third-party motion generators from various market areas, and this is what we've discussed so far. What you may not know or not notice is that we are not limited to GNSS. Increasingly, GNSS is used with other signals and sensors. Spirent supplies test and evaluation solutions that provide coherent emulation of whatever combination of signals and sensors are required. To do so, we work with industry leaders across the sectors to provide integrated solutions, leading to co-simulation. Our aim is to provide solutions to PNT, position, navigation, and test challenges that are realistic and support multiple signals and sensors, not only GNSS. We do this as part through internal development and through partnering with industry leaders. With that, I'll pass the ball to Roman, and thank you very much.
So thank you, Rafael and AJ, and now let's move on to the Q&A. So we have some questions already, and we'll try to get to as many as possible. So the first one is a question on, so what PNT accuracy, availability, integrity, and continuity is required? So in other words, can we quantify what level of accuracy, availability, integrity, and continuity is required for autonomous vehicles? So I guess that's a question for Rafael.
Okay. Yeah, so as I already mentioned during the presentation, the more complex the environment and the more agents that there are in the environment, the more accuracy is required. With autonomous vehicles, if we just focus on cars driving on a motorway, we expect them to have a decimeter level of accuracy, which is tens of centimeters, whereas in urban environments, they need to have centimeter accuracy. And the main reason for this is because we need to make sure, as I already mentioned in the presentation, that the information which is given to the control system is accurate, so that when the decision is taken, it's taken properly, so that the vehicle is in the right lane, the distance is measured between the vehicles is accurate, so the maneuvers can be done accordingly.
So thanks, Rafael. Now I'll take the next question, which is on the sensors. So you showed us the different sensors on autonomous vehicles. What sensors can Spirent simulate today, and is there any plan to add more in the future?
All right, let me take that question. So as I talked about it on the slides, As of today, we can support GNSS, we can support inertial measurement units, and then we can support wheel takes, and the interfaces can be pretty flexible. Going forward, we definitely see a need for other sensors to be integrated alongside GNSS and inertial, and we intend to do that through some of our internal development and some by partnering with other companies.
So I'll take the last question, and this time the question is, I think, for Raphael again on timing synchronization. So why is timing synchronization important for an autonomous vehicle?
Okay, thanks, Roman. So timing synchronization is of critical importance, mainly because vehicles need to know where the other vehicles are on a common time. So just to give you an example, if you have a junction and a vehicle is sending its position, saying that it's approaching the crossroad and it's about to carry on, then the other vehicle, which is coming from the other side of the crossroad, needs to know that the vehicle is, say, 5 or 10 meters away, and there is no way that they can take the crossroad together. So the second vehicle would have to stop. Now, if there's a timing delay, then the position might come when it's too late. So the vehicle which sent the signal might already be on the junction, and that would create a hazard.
Thanks for this answer. And also, I'd like to thank AJ for the presentation and the answers. And I'd like to thank you all the participants for attending this webinar today. So we are closing. The webinar has been recorded, and you will be able to access the recording within 24 hours using the same link, audience, as that was sent to you earlier. So thank you again for joining, and we look forward to seeing you at future events.